Okay, so we'll begin the all right. Okay, so the poll on Campus Wire has been going, and it is there's broad support for changing the schedule around over 90%. And so we will go ahead and hold a lecture on Friday. I'm actually not available at this time, 4 o'clock on Friday. So I'll probably schedule it for noon to 2 p.m. on Friday, and I'll put and if you're not able to attend live, I'll record the video and you'll just have to watch it. Okay. And I will, what I will do is on CCLE, I will put Friday's lecture. I will still keep it in week 6. And this is just to prevent people from getting confused and entering the wrong lecture quiz answers to the wrong lecture. Because generally, I only have one lecture quiz open at a time, okay? But what I'll do is I will keep Wednesday's lecture quiz open for a long time, and I'll also keep Friday's lecture quiz. So I think Wednesday's lecture quiz I'll keep open until I guess next Wednesday, and I'll also keep on Friday I'll keep it open to Wednesday. So both quizzes will be open at the same time, and to prevent people from getting confused and accidentally answering Friday's lecture answers into Wednesdays, because it happens a lot every quarter. If I have multiple quizzes open, people get mixed up. So I'll put the lecture on Friday, but I'll post it in week 6. Okay. And so I'll see you guys on Friday if you're able to attend live, and if you're not, just you'll have to watch the video. Okay. All right. Are there any questions before we get started here? Okay. Oh, there's a question. It's about the final exam. Is it 2 hours or 3 hours? I'm planning for it to be 2 hours. I suppose, well, I'll write it for 2 hours, and I suppose if we need some extra time, I can grant extra time as it's happening. And again, the final exam is live, so we do have a little bit of that flexibility to kind of grant extra time as it's happening. Okay. And when will homework 5 be due? Sorry, next week I have other classes, final and project I need to plan. So when will homework 5 be due? So so right now, homework 4 is due this week. Okay, so homework 5 I will release, and it'll probably be due on Friday of week 6. That's going to be the plan. Okay, so I'll release homework 5 pretty soon. You'll see it posted up in week 6, and it will be, I'll make it due Friday of week 6. Okay, that's on calendar there. Okay. All right, so let's talk about optimization. So today we're going to cover numeric optimization. So our last lecture we covered, we introduced numeric methods as a way to get an approximate answer for something. And our first set of numeric methods were on root finding, where we find zeros of a function, right? Where the function is equal to 0. And now we can expand that and do numeric optimization. Okay, and so we're going to just cover a few basic things in optimization. And optimization is all about finding where a function either has a local min or a local maximum. Okay, and so our first set is going to be derivative-based numeric optimization. Okay, so derivative-based numeric optimization. And again, numeric optimization, we're trying to find where the function is a minimum or a maximum or something like that. A lot of the algorithms that we use are designed for finding a local minimum, say f of the minimum of f of x. And if you want to find a maximum, you can use the exact same algorithm. And all you do is you just take the function and you multiply it by -1, okay? And then you just find the minimum of the function multiplied by -1, and that location will be the exact same place as where you have a maximum, right? So whatever works for finding a local minimum, we can use to find a local maximum as well, okay? All right, and so derivative-based numeric optimization is just kind of the natural next step after you learn root finding methods, right? So root finding methods, we found is used to find where the function is equal to 0. And so when we use a derivative-based method, all we do is we take the function f, we find the derivative of f prime, okay? And then we apply a root finding method to f prime. And so where you have f prime equal to 0, okay, the when you find where the derivative is equal to 0, those are going to be your critical points, right? And that's where the slope is equal to 0, and that's going to either have to be a local minimum, a local maximum, or some kind of saddle point, okay? Because that's generally where functions are equal to where the derivative is equal to 0, right? And so the process looks like this, right? Find the derivative of f of x, okay? And then any of the root finding algorithms that we learned in our last lecture can work here, right? So you find f prime, you find the roots of f prime, and then you evaluate those critical points, right? And so a very common method is to use Newton-Raphson method, okay? So if you say, oh, I want to find the roots of f prime of x using Newton-Raphson method, okay? Then it works like this, right? So you're going to say, if we find the roots of f prime, then that will give us a local min or local max of the original function f of x, right? And so for Newton-Raphson method, you can start at some location x sub 0 that's expected to be close enough to a local min or local max. And then the next value is going to be your current value xn minus f prime of x divided by f double prime of x, right? So minus the first derivative at x of n divided by the second derivative at x of n. Okay, and this is pretty much the if you look back to your notes on root finding, the root finding method for Newton-Raphson is just f divided by f prime, and that will find the roots of f. And basically, now we're finding the roots of f prime, so we're doing f prime divided by the derivative of f prime, which is going to be f double prime. Okay, and so in order for this to work, f of x needs to be twice differentiable, all right? And then again, in order for the sequence to work, f double prime cannot be 0 for any of the x of n's that we check, okay? And or you also don't want it to be like very, very close to 0 where you get, where you're dividing by something incredibly small and this number gets huge, right? And f double prime is allowed to be 0, but it just can't be 0 in the sequence of x of n's that get evaluated. So as you evaluate, different locations, x of n plus 1, x of n plus 2, et cetera, f double prime, whatever number you put in that denominator just is not allowed to be 0. Okay, so let's say we wanted to find the critical points, the local min or local max of this function here, 0.25x to the fourth minus 0.5x squared, okay? So we're going to say, all right, let's find the first derivative of this. First derivative, apply kind of, the 4 comes down and you reduce the power. So that becomes x cubed. This becomes minus x cubed minus x. And then we take the second derivative. So the derivative of x cubed is 3x squared. The derivative of minus x is minus 1. And so we use that and we're going to find find the roots of f prime of x. Okay, and so all we're going to do is just apply this algorithm iteratively, we start at some arbitrary location x sub n, and we find the next value in our iterative sequence by applying the Newton-Raphson method. So, so this is what the function looks like. And so there's technically 3 values where we would have a, where the derivative of f would equal 0, right? We have a local min here, a local max there, and a local min here. And so we would have 3 critical points. And basically, by applying Newton-Raphson method to the derivative, it should identify at least one, or it should identify one of these critical points, depending on, where our starting location is. Okay, so here I'm going to start off, my first value is going to be 2.1. Okay, so I start off at 2.1, which is going to be over here. And, we'll find basically where the function is going to have a local minimum. Okay, so here we plug in f prime. F double prime is this 3x squared minus 1. All right, so our old value is 2.1. Our next value is going to be x old minus f prime of x old divided by f double prime. And then we run the Newton-Raphson algorithm applied. So we're going to just say whenever x new minus x old is greater than, as long as it's greater than the tolerance, which we're going to set to 10 to the minus 6, just iterate and do the algorithm. Okay, and so we're going to do x old minus f prime of x old divided by f double prime of x old. That's all we're doing, is just applying this. And it runs and it identifies a local min or local max at some critical point at 1. Okay, and we can see, oh yes, that is indeed going to be a local minimum. Okay, and that's with the starting location of 2.1. Okay, what if I start at 0.9? Okay, so 0.9 is over here. Okay, let's go ahead and let it run. We start off at 0.9, and it also finds the value 1. If I start off at some other point, 0.1, so I'm starting here, and I say go ahead and find the thing, it runs, whoops. And when it runs, the value is just about 0, okay? And we can see in our graph that we do have a local max at 0, right? And so we can see that depending on our starting location, we're going to end up finding different critical points, okay? And so you kind of have to test this out, and you don't know. So that's one of the issues with Newton-Raphson method, is that you don't know where you're going to end up, okay? Depending on where you start, you can end up with at a different location, and you don't really know where you're going to end up unless you have a picture of the graph, okay, which you don't always have, or you know something else about the graph. But a lot of times, this is a simple function, so we're able to kind of graph it, okay, and we're able to just visually see where the local mins and local maxes are, right? This is a luxury that we often don't have in real life. In real life, the function is not as simple as this, and the function might be more difficult, and we might not visually know. And so there's definitely a lot of limitations with this method. You can use it to find critical points, but there's no guarantee that you're going to find kind of all of them. And there's also, you really have no idea which critical point you're going to find, okay? And so here we started off at -10, and it finds the critical point at -1, okay? And but it works, okay? It works, and it will, again, depending on the properties of the function, depending, if kind of all of these things line up, it can be useful, and it can quickly identify a critical point, which will correspond to either a local min or a local maximum, okay? But again, like Newton-Raphson method is not guaranteed to find the roots of a function. Newton-Raphson method is not guaranteed to find, to converge to a local min or local max, okay? But if you are able to find the derivative, you are able to apply any of the root finding methods from the last lesson. So if you want to say apply bisection method, or apply, you know, even something like fixed point iteration, it can be done. So any kind of root finding method can be applied to the derivative, and that will, you know, in theory, give you the critical points of the function, which hopefully corresponds to either local mins or local maxes. All right, and again, so in our last lecture, we talked about estimating the derivative numerically, right? So here we found the derivative analytically, okay? We found the derivative analytically, but in our last lecture, we talked about estimating the derivative numerically, and that you can also use that in any of these root finding methods, right? So, or not root finding, optimization methods. So if you want to find where the function has a derivative equal to 0, you don't actually have to find the analytic derivative. You can use the function that outputs an estimate of the derivative, okay? Because as far as the computer knows, right, all it's doing is it's just plugging in a value here and it's plugging in a value here, okay? So it doesn't actually know that this is, an analytic function or this is an analytic function, okay? We wrote a function in our last lecture where you plug in a number and it gives an estimate of the derivative, okay? And you can do the same thing. You can, if you create a function that you plug in a number and it gives an estimate of the derivative, you can also create another function that you plug in a number and it gives an estimate of the second derivative, okay? And you can do those things, and you can still apply the optimization method, and it will still it'll still work, okay? Let me go ahead and give you your first view quiz answer for today. Today's first view quiz answer is the letter B, B as in bear. B as in bear is your first view quiz answer for today. Okay, golden section search. This is another method for finding the local min of a function. And again, if you want, you can use it to find the local max of a function by just multiplying the function and multiplying it by -1. All right, so if you recall what the golden ratio is, the golden ratio is the ratio between one edge of this rectangle and the other edge of the rectangle. Okay, so maybe the long edge divided by the short edge, okay, in such a way that when you do 1 plus x divided by 1, okay, it's going to have the same ratio as basically 1 over x. Okay, so these proportions apply. So when you take the ratio between the red line to the blue line, which is 1 plus x divided by 1, it's going to have the same ratio as the long edge over the short, whoops. So 1 divided by over x, okay? So the red line over the blue line, right? And now this yellow line is 1 minus x, okay? And the same kind of ratios will hold up, okay? So the ratio between red and blue over here is the same ratios as red and blue over here, okay? So 1 over x is equal to 1 plus x over 1, okay? That is, or blue over red, 1 over 1 plus x is equal to x over 1 here, okay? And so if we solve for that, right? If we say 1 over 1 plus x is equal to x, 1 over 1 plus x is equal to x, then we can find using the quadratic formula, right? So we move some terms around, we multiply both sides by 1 plus x, we subtract 1 from both sides, and we say, okay, let's solve for x, okay? X is going to be -1 plus or minus the square root of 5 over 2, okay? And so this quantity ends up being 0.618, okay? And here we only accepted the plus side because x is a positive quantity in our picture, right? So x is 0.618, something around there, okay? So the red line, it has a length of 1.618, blue has a length of 1, and yellow has a length of 0.618, right? And we can see that indeed, if I do 1 divided by 1 plus x, 1 divided by 1.618, I get 0.618, okay? And also, what's also going to hold is if you do, if you take x squared, okay, 0.618 squared, you're going to get the quantity 1 minus 0.618, okay? So 0.618 is equal to 1 minus 0.618. So 0.382 is approximately equal to 0.618, right? This is just rounded off to 3 decimal places, but you know, the golden ratio given by this quantity, -1 plus the square root of 5 divided by 2, you know, that quantity is the golden ratio. Okay. And so we're going to take advantage of this thing, that 1 minus x is equal to the same thing as x squared, to determine points to evaluate, to figure out kind of where our local mins could be, right? Okay, so let's say we have this function, okay? We're going to just have this quadratic function, x squared minus 0.8x, okay? And just visually, we can see, okay, the minimum happens when x is 0.4, okay? But here we're going to go ahead and we're going to just start off with some interval. Let's say we're going to go from 0 to 1 here, 0 to 1 here. And what we're going to try to do is we're going to try to kind of bracket off an interval and shrink. So it's kind of like bisection method. We're going to kind of bracket off areas, and we're going to try to evaluate and figure out where the minimum is, okay? Now, again, the reality is we don't have this nice visual picture, okay? Nice visual picture where, you know, we can look at it and say, oh, the minimum's at 0.4, okay? We're just going to pretend that the function exists. We're able to evaluate the function at certain locations, and we're going to use this bracketing method to try to identify where the minimum might be, okay? So first I'm going to start off at 0 and 1, and these will kind of give us some nice little numbers. And what we're going to do is we're going to evaluate this distance has a distance of 1, and we're going to pick a location, you know, the golden ratio between 0 and 1 going this way, and a golden ratio between 0 and 1 and going the other way, right? And so basically we have the lower bound, the left side, and the upper bound, okay? That's going to be a distance of u minus L. And if our golden ratio, if I denote that with the symbol phi as 0.618, okay, we're going to find this location, all right, which is going to be the lower bound plus phi times this distance. That's going to give us x1. And then we're going to find this location, x2, which is going to be the upper bound minus phi times this distance. Okay, so in our case, the lower bound is at 0, the upper bound is at 1. So this distance is 1, u times u minus L has a distance of 1. And so phi times 1 is 0.618. We're going to add that to the lower bound of 0. So our x1 is going to be around at 0.618. And then our x2 is going to be 1 minus phi times the distance. So 1 minus 0.618 times 1, and that gives me 0.382. Okay, so I'm going to be searching a value at x1 and at x2. Is that all right? So this is kind of what our picture now looks like. Okay, so we have the lower bound, we have the upper bound, and we have locations x1 and x2. And what we do is now we evaluate the function at x1 and we evaluate the function at x2. We evaluate the function at x1 and the function at x2. And when we evaluate these 2 points, we see, oh, the function at x1 is greater than the function location, than the function at location x2. Okay, so based on this, we have these regions, okay, where we say, so I guess what we're going to say is we know that there has to be a local minimum somewhere between the lower bound and upper bound. That's kind of the starting criteria, is that between the lower bound and the upper bound, there's a minimum value. And the question is if I know x2 has a smaller value than x1, where does the minimum value have to be? Okay. Well, based on this, we can say the minimum value cannot be between x1 and the upper bound. Okay, because we're going to just say, there's one minimum somewhere in this bracket. Okay, there's one minimum somewhere in this bracket here between 0 and 1. Okay, and so, again, visually, we can see this, but even if we can't see this line, if we know that x1 is higher than x2, I mean, the function at x1 is greater than the function at x2, we know that the minimum is not going to be between x1 and the upper bound. Why? Because we know already that there's a value to the left of x1 that is where the function has a lower value than f of x1. Okay, so because we know because f of x1 is greater than f of x2, we know that the minimum has to lie between L and x1. Okay, the minimum cannot be, right? If we're assuming that there's one minimum value between the lower bound and the upper bound, okay, we know that the minimum value cannot be to the right of x1 because we know that a value to the left of x1 already has a value that's lower than f of x1. Okay, so because there's a value over here that's lower, we know that there's not going to be another value over here that's lower than x1. Okay, so we can completely eliminate this side to the right. Okay, and now my interval is going to go from 0 to 0.618. Is that okay? So the logic here is we know that there's got to be one minimum value between 0 and 1. And because we know there's a value over here on this side that's lower than the value over here, we know that we can eliminate this side. Okay, so what we do now is my next values, or my next interval goes from 0 to 0.618, okay? And what we're going to do is we're going to set, okay, this right side bound, x1, which used to be x1, this is going to be my new upper bound. And then this value here that used to be x2 will become the new x1. Okay, so remember back here, it goes lower bound, x2, x1, and upper bound. Okay, and so when you do that, we're still going to have a lower bound. This is my new upper bound. Okay, and this location at 0.382 is now going to be my new x1. Okay, and that's kind of the genius of using the golden ratio here, is that I don't need to pick two new points here. Okay, I can reuse the point that I calculated earlier, right? So in the last iteration, I calculated x1 and x2, and I evaluated the function at x1 and x2. Okay, so I evaluated the function right here, and I can just reuse that. Okay, anytime you can reuse a value in an algorithm, we want to do that. We don't want to have to recalculate a new location in the middle and recalculate the function at that new location. So I can just reuse that. Okay, because why? Because phi squared is the same thing as 1 minus phi, right? So this location over here, which is 1 minus phi, this is now equivalent to doing phi L minus u times phi. Okay, this location, this distance is from 0 to 0.618. If I do 0.618 squared, I'm going to get 0.382, and that's what I have here. Okay, and 0.382 is equivalent of doing 1 minus 0.618. Okay, so the genius of the golden section search is that we use the golden ratio to determine the inner points. X2 has a value of 0.382. That's going to be equal to doing 0.618 squared, phi squared, right? So the new x1, if we were to just recalculate these ourselves, we would take the lower bound times phi times kind of this new distance here. This new distance is 0.618. That's going to give me 0.618 squared, which is equal to 0.382, okay? And so we can reuse the old x2 and the old fx2. That's going to become the new x1 and the new f of x1. So I don't have to re-identify these points, and I don't have to recalculate the function at that location, okay? I do need to calculate a new value, which is going to be, basically 0.618 times 0.618, 0.382 less than over here, okay? And so if I zoom in, I'm going to have to calculate over here from 0 to, 0.618. And so if I do 0 minus 0.382, I mean, 0.618 minus 0.382, I'm going to get 0.236, and that's going to be the new x2 value in the middle. Okay, so I've eliminated this side. This is kind of my new lower bound, and my new upper bound. This is x1, and this is my new x2 value. Okay, so this value I'm reusing from last time. This is a new location in the middle that I'm going to calculate, and I calculate the function at this location here. Okay, and so when we look at this, we can see that this side is greater than this side, okay? And therefore, we can completely eliminate everything to the left of the new x2, right? So we can completely eliminate everything to the new, left of the new x2, again, because we know that there's one minimum value between 0 and 0.618, and if we know that this value is lower than this, we know that the minimum value can't be to the left of this because there's a value to the right of it that's lower than this. So we're going to completely eliminate that, okay? And so that boundary over here is going to become our new lower bound. The upper bound remains the upper bound. And this location down here is going to become kind of one of the inner values, the new x2 value. And we have to figure out the x1 value, which is going to be over here. Okay. Is this all right as far as what's happening here? So it's a bracketing method, but we're using the golden ratio to find the inner points. And when we find the inner points, we evaluate the function there to kind of eliminate one side or the other. And then the genius is that we can reuse kind of the previous point, the previously calculated points. Okay. So here we go. So we have this. We're going to delete, and not delete, but we're going to eliminate everything to the right because this is greater than this side. So we do that. Here's going to be kind of our new center points. The one to the left is a little bit greater than the one to the right. So we eliminate everything to the left, and we're going to recalculate. And so these two things are actually very close in quantity, but they are not exactly the same. The one on the left is a little bit greater. We evaluate the stuff on the right. Okay, we evaluate over there. And we can see that this bracketed area gets smaller and smaller. Okay, and we can see that it's kind of zeroing in, getting closer and closer to 0.4. Okay, so here's how it starts. So, we eliminate a side. And so notice that this one of the inner lines, right, the line that doesn't get eliminated becomes kind of the next point, right? So here we eliminate that side, and we establish this. We eliminate this side, and we use that. Whoops, and then we eliminate that, and we get that, and so on and so forth. Okay, and it's going to kind of continue to bracket down until we get down to the minimum value there. Okay, golden section search is very robust. If a minimum lies within the interval, it will find the minimum. If the minimum actually lies on the boundary, it will converge to the boundary point, okay? And if multiple local minimum do exist within the interval, the algorithm will just converge to one of them, okay? All right, there are multiple termination conditions, and a possible choice is when the difference between the upper and lower bounds are less than some arbitrary tolerance value. Then you just kind of take that and you kind of take the average, the midpoint of the upper and lower bounds at that point. Okay, this is code that will conduct golden section search. Okay, and so you take some function f that you're trying to minimize. You have a lower bound, an upper bound, and then the tolerance level which is when we will quit, okay? And so this will quit, the iterations will continue to run as long as the difference between the upper and lower bound are greater than the tolerance, okay? And then at the end, when it does quit, the value it returns will be the midpoint of the upper and lower bounds, okay? The value that it's going to return is lower plus upper divided by 2, the midpoint of the lower and upper bounds. Okay, so we put in and we say, all right, let's figure out the quantity of the golden ratio, okay, which is going to be this quantity phi, okay. And again, the arrangement of points goes lower x2, x1, upper, all right. And so x1 is going to be lower plus phi times upper minus lower. x2 is going to be upper minus phi times upper minus lower. And then we're going to evaluate the function f at x1, and that's going to give me the value f1. F at x2 gives me the value f2. We're going to start off with 0 iterations, and we're going to say if f2 is greater than f1, okay, if f at location 2 is greater than location at f1, we are going to eliminate the lower, this lower side, right? So x2 is going to become the new lower bound. x1 becomes the new x2. F at x1 becomes the new f2. We have to calculate the new x1 value, which is going to be lower plus phi times upper minus lower, now that we have a new lower bound. And we're going to calculate a new value for f1, which is going to be f at the new x1 value. Okay, so we'll do that. If f2 is not greater than f1, which means either f1 is less than or equal to f2, then we will eliminate, we're going to eliminate this side. Okay, so x1 becomes the new upper bound. x2 becomes the new x1. This becomes the new x1. F at x2 becomes the new f at x1. And we calculate a new kind of x2 value, which is going to be upper minus phi times upper minus lower. We calculate the new value of f2 of f at x2. And we increment our iterations, and then we go and we check, is the difference between upper minus lower less than my tolerance? If not, continue, and we just kind of continue the iterative process. Okay, and so this runs and runs and runs, and then eventually it spits out whatever your value is. Okay, so if I plug in this function x squared minus 0.8x, where we know the true minimum is at 0.4, and I test it out using a tolerance of 10 to the 9 minus 5, it converges and it says, okay, your minimum is at 0.399999, and it took 24 iterations. If I say, you know, I want a tolerance of 10 to the minus 6, it takes me 29 iterations. If I want a tolerance of 10 to the minus 7, it takes me 34 iterations. 10 to the minus 8, it takes me another 5 iterations, 39 iterations. Okay. So it seems consistently the number of iterations goes up by 5 every extra decimal value of precision that I want. Okay. And so we can think, you know, why is it that every time I want an extra decimal point of precision, the number of iterations go up by 5? Well, it shrinks. The rate of convergence is linear, okay? And every iteration we do it, the width of the interval shrinks by a factor of 0.618, right? The next interval width is 0.618 times the previous interval's width, right? And so if you take 0.618 and raise it to the 5th power, you're going to get something around 0.1, a little bit less than that, 0.09. And so basically, if you want to shrink it by a factor of 10, you're going to require around 5 iterations, okay? Doing another 5 iterations will shrink it by, I guess, almost like a factor of 11, okay? It'll give you, the width of the interval will be 9% of its original width. Okay, is that all right as far as golden section search goes? Any questions there? Okay. Thanks for your enthusiastic response there. But all right, well, that's golden section search. And yes, thank you for your thumbs up. Okay. All right, let's do another method, okay? And we're going to look at coordinate descent. So these previous methods, they work well. And so far we've been looking at one-dimensional functions, okay? And honestly, optimizing a one-dimensional function is actually pretty easy, okay? In that you can just kind of brute force the function. Generally, if you have a function in one dimension, you can just calculate the function at a whole bunch of locations and just pick the lowest one. This is known as doing a grid search, right? So you can say, all right, let's just evaluate the function at every kind of 0.001, right? So here I've got some function at x squared minus 0.8 times x, and I'm going to calculate 6,000 locations between -3 and +3, okay? And we're just going to evaluate the function at every single one of these 6,000 locations, okay? And we just say, okay, which of those values is the smallest one, produced the smallest value of f of x, right? So I'm just going to say, all right, here's x. It goes from -3 to +3. I evaluated this at 6,001 locations. We're going to calculate f of x at every single one of these x locations. Which one's the smallest? It said the 3,401 first value is, and what's the value of x there? 0.4, okay? This is like a, quote, brute force method, right? You're just evaluating the function at a whole bunch of points, and you're saying, which one's the smallest? Ah, it's this one. And there you go. That's known as a grid search. I would barely even call this an optimization method. This is just a brute force approach. You just evaluate the function everywhere, and you just say, which one's the smallest? That's the one we're going to go with, okay? That's called a grid search. It's a little bit of a brute force method. But if it's a univariate function, it's not too bad, right? It's not too hard to do, because univariate functions, 6,000 locations, it takes your computer a couple of seconds to do that, and it's not so hard, right? What if we wanted to do this, but for a two-dimensional function, okay? A two-dimensional function. So we're going to search this square from -3, -3 to +3, +3, right? So I've got a square 6 wide, 6 tall, okay? How many, if I wanted to do a grid search, do a brute force search there, how many locations would I have to evaluate, right? If I have to evaluate 6,000 points in the x direction and 6,000 points in the y direction, we're going to have a total of 36 million locations to evaluate, right? And so to try to take this brute force approach in a two-dimensional function is a lot harder, okay? And these earlier methods, golden section search and derivative-based numeric optimization, so far, like we've only talked about using them in unidimensional settings, functions of one variable, right? So if we were to try to attempt this at apply just this brute force grid search method to a higher dimensional function, now I've got 36 million locations to evaluate, right? What if you have a function in 3 dimensions? A function in 3 dimensions, you take 36 million times 6, that would give us what? 216 billion locations to evaluate. And that would be a 6 by 6 by 6 cube, right? 6 by 6 by 6 cube, around 216 billion locations. That might take your computer a very long time to evaluate. So this brute force grid search method is not going to work very well in higher dimensional settings. So what we're going to do is we can do coordinate descent. Okay, we're going to do coordinate descent. And what coordinate descent does is it says, oh, you want to find the minimum of this multi-dimensional function. Okay, right? So let's say we have a 2-dimensional function and we want to find the minimum of a 2-dimensional function. Okay, what it's going to do, what coordinate descent does, it says, hey, you know what? Rather than trying to find the minimum of this two-dimensional function, what if we reduced the two-dimensional function down to a univariate function, right? Let's keep one of the variables constant, right? You got a function of two variables. If you keep one of the variables constant, then you now have a function of one variable. And we know how to optimize functions of one variable, right? We can do derivative-based numeric optimization. We can do golden section search. We can even do grid search on a one-dimensional function. That's not so bad, okay? So what we're going to do is we're going to take our higher dimensional function, a two-dimensional function. We're going to kind of hold all but one variable constant, right? So we're going to select one of the variables to minimize. All of the other variables are going to be held constant, okay? And that reduces the multivariate function down to a univariate function, okay? Then we perform minimization on a univariate function, which we know how to do, okay? We know how to do minimization on a univariate function, okay? And so we find the minimum for the function in one direction, okay? And then what we do, once we do that, we will lock that variable in place, and then we're going to find minimization for the other direction, okay? And then we do this iteratively. So we minimize one variable, lock it in, minimize the next variable, lock it in, and then we kind of iterate back and forth, okay? And so to kind of illustrate this, so I talked about this here. I don't know if it makes a whole lot of sense. So I have some code here that will demonstrate, and I posted this on CCLE, so you can follow along as well. Although I think I need to change the settings on this thing. Force and download. I think that should force you to download that. Okay, so I'm going to load up. Oh, I need to also load up the golden section search. Sorry, I forgot to upload this. You're going to get an error if you try to. So the golden section search code that does univariate optimization is up here as well. Okay, so golden section search code. Okay, so we have coordinate descent R script and the golden section search R script. All right, so we'll go ahead and load that in. Library plotly. Okay, and then so here's going to be the function that I want to optimize. Okay, this is my function, and we're actually going to plot this. Okay, and here I'm using plotly, and you guys can see this, I hope. So plotly is this kind of cool little thing. So this is what we would call an ellipsoid. So it's basically like a bowl. Okay, it's basically a bowl. You think of I'm sorry, not an ellipsoid, paraboloid, right? You think of a parabola, but then you think, okay, let's make a 3D version of a parabola. Okay, and so basically you have so from the top down, you know, we're looking for this minimum here, which is somewhere around there. Okay. And basically, if you were to take slices, you get little ellipses. And, you know, this profile view looks like this, and the minimum is somewhere around here. Okay. So this is pretty cool, right? This is plotly. We have kind of a 3D plot of the function that we are trying to minimize. Okay, so this is, so let me just demonstrate how coordinate descent works. We're going to start off at some arbitrary location. Okay. And this script is intentionally very, very poorly written. Okay, this script is written very poorly because your homework, you have to, what did I say? In your homework, you have to write coordinate descent. Okay, and so I didn't want to like write out the entire coordinate descent algorithm for you guys in this script. So I'm just kind of doing this very step-by-step. Not really an algorithm, but just doing each step of the coordinate descent algorithm manually. Okay, so anyway, I'm just going to plot the function, and this is going to be my starting location. It's going to be at -1, 1.5. Okay, so why does it look like this? Okay, so this is, I guess here's the orientation that we're accustomed to. X is at -1 and Y is at 1.5. Okay, this is going to be my starting location. And so what we're going to do, okay, the original function is x squared minus 2x minus 0.5xy plus 2.5y squared. Maybe I should bring this over here and write this out. So give me a second. Okay, so this is the function that we're trying to optimize. It's a function of x and y. Okay, so the function is x squared minus 2x minus 0.5xy plus 2.5y squared. Okay, and then so what I'm going to do is my initial point x0 y0 is equal to -1 comma 1.5. Okay, and what I'm going to do is I'm going to create a function. Okay, we're going to call this g1 for g at iteration 1. It's going to be a function of x. Okay, and basically I'm going to plug in y equal to 1.5. Okay, so I'm taking this and I'm plugging in 0.5x times 1.5 plus 2.5. Wherever I see a y, I'm going to plug in 1.5. Okay, and so this becomes, I didn't even bother calculating this out, but this now becomes just a function of x, right? G1 is just a function of x. It becomes x squared minus, what is this? 0.5 times 1.5, that's 0.75. So I think I get negative 2.75x plus, I don't know, some constant. Okay, is that right? I think I might have made a mistake here. Okay, and then basically, so now I have a function of one variable, and then we do a univariate optimization here. Okay, so we're going to do univariate optimization on this function, and when we do that, we get x equal to some value. Okay, so here I'm going to so this is the function. So I'm going to hold y equal to 1.5 constant, and basically so this adds a trace to the line, and basically now I have a univariate function right here where y is held to be equal to 1.5, and we're going to find what's the minimum of this function, right? So we're going to say, what is the minimum of this function? The minimum of this function is right here. Okay, and we can find that location. I'm going to just use golden section search. Okay, so we're going to apply golden section search to the function g at iteration 1, where the lower bound is from -1.5 to 2 on x. And when we do this, it says, oh, you know what? Your minimum location is when x is equal to 1.375, right? So when you do this, you get min at x equal to 1.375. Okay, so I will go ahead and add that marker right here. Okay, so this is now the minimum, okay, of this univariate function. The univariate function is this x squared minus 2.75x plus some number. The minimum happens at x equal to 1.375, which is plotted as this white dot right here. Okay, and now we're going to hold x equal to 1.375 constant. Okay, so we're going to call this G at iteration 1b. Okay, this is going to be a function of y because I'm going to plug in x equal to 1.375 wherever I see an x. Okay, so I'm going to have 1.375 squared minus 2 times 1.375. These are just constants, right? Minus 0.5 times 1.375 times y plus 2.5 y squared, right? So this G at iteration 1b is going to be some constant minus 0.5 times 0.375. I don't know what that is. What is that? 0.6725. .68. I don't know. What is that? Okay. Is it 0.5 times 1.375? 0.6875. Okay, 6875 plus 2.5 y squared. Okay, so you get something here, and you minimize this, right? Find a minimum at y equal to something. Okay, so here's the function G at iteration 1b. I'm basically plugging in x equal to 1.375. We plug that in, and we get all of these numbers. Okay, and I'm going to add that trace here. And so basically, now that I'm holding the function constant, okay, we're going to function is held constant at x equal to 1.375. We're going to find the minimum of this white line. Okay, where's the minimum of the white line located? The location, the minimum of that white line is located at y1 or at y equal to 0.1375. Okay, so this is minimized at y equal to 0.1375. Okay. And so, so I'm going to go ahead and plug that in. Okay, we're going to add a marker location at y equal to 0.1375. And so that is located at this yellow dot right here. So the minimum of this white parabola, unidimensional, it's one function of one dimension. Okay, because we've locked in the x value. The minimum of this white function is right here at this yellow dot. Okay. All right, and so we're going to lock that in. All right, and okay, and so we repeat this. Okay, so now I'm going to find the function where y is held constant at 0.1375. Okay, and let's add that trace here. Okay, so y held at 0.1375. That's this yellow line here. And we say, okay, let's minimize this yellow line. Right, where's this the minimum of this yellow line going to be? Okay. So we apply golden section search, and it says that's minimized when x is equal to 1.034. Okay, and let's add that. Okay, so that's located right. Okay, as I zoom in, so we can see we're getting closer and closer to the center here, right? And so this yellow line here is located at x equal to 1.373. 1.03475. Okay, right there. Okay, and we continue this, right? So this is where my code stops, but we would lock this value in and find there would be some line parallel to this white line, and we would minimize that, and that will get us closer and closer to the minimum of the two-dimensional function. Does that make sense? How coordinate descent works, right? So you have this high dimensional function or two-dimensional function, but we're going to lock in one variable at a time. And when we lock in one variable at a time, we have now a unidimensional function, and we know how to optimize unidimensional functions. We can use golden section search. We can use, Newton-Raphson or whatever we want. Okay, here I've been using golden section search. And it gives me minimums, and we can go plug those in there, right? What's the stopping criteria? Oh yeah, I didn't quite mention it, but basically, you would just say when the value of the function at your next iteration, you know, the change in the value of the function is less than some tolerance level. Basically when the change in the function is close to 0, that's basically where you've reached like basically the derivative is 0, right? So it could happen depending on your function. If you just have this very flat region, it's possible that you end up getting stuck in a very flat region, right? All of these things kind of require that there's a little bit of like slope in the function. So if your function has kind of this very broad flat region, you can kind of get stuck somewhere there. But you know, ideally, you're just going to keep iterating until you know, your next iteration doesn't change the value of the function, right? Or the change in the function is less than some tolerance level, then you can stop. All right, so this is coordinate descent, and I hope this visualization helps make a little bit more sense of basically what we've written here. Okay, any questions there? We're good, we're gonna keep going. Did I already give you your second view quiz answer? Not yet. Okay, let me go ahead and give you second view quiz answer is D. D as in dog. D as in dog is your second view quiz answer for today. D as in dog. All right, we have another optimization method, numeric optimization method, right? This is just a whole bunch of numeric optimization stuff. Okay, this one is the Nelder-Mead method. Nelder-Mead method. And these sections of my notes is based very much off of the notes of Professor Henry Gavin at Duke University. So credit where credit is due. Okay, again, Nelder-Mead, just like all of these other optimization methods we've looked at, is a numeric method. Okay, and it can be used to find the minimum or a maximum of some multi-dimensional function, right? What it is it's a direct search method, okay? So it doesn't do derivatives, and what it does is it just calculates the value of the function and it compares to other values, and it uses that to try to figure out where the minimum is, okay? Search works well, not guaranteed to converge. Okay, and so the Nelder-Mead method uses what's called a simplex, okay? And that's basically a shape consisting of n+1 vertices. So if your function is in 2 dimensions, your simplex is a triangle. If your function is in 3 dimensions, your simplex has 4 vertices, which would be a pyramid or a tetrahedron, okay? And if your function is in 4 dimensions, okay, 4-dimensional function, it's called a 5-cell pentachoron, which looks kind of like this, but strange, right? And so this is a 3-dimensional pentachoron projection of a 5-cell, which, you know, breaks your brain if you try to think of it. It's performing a simple rotation, but it's doing this, right? So anyway, whatever it is, right? So in 2 dimensions, your simplex is a triangle. So we'll just look at the 2-dimensional triangle method, but if you needed to generalize to a higher dimensional thing, you can kind of imagine how this works, okay? And so you start off with your 2-dimensional function, and what we want to do is we want to find a local minimum, okay? And so we begin with kind of 3 arbitrarily selected points in 2D to form our simplex, okay? So we just pick 3 arbitrary points, and what we're going to do is we're going to do these steps. We're going to sort the values of the points. We'll do a reflection. We might do an extension. We might do a contraction. We might do a shrink, okay? And each one we do at least a reflection, and then what we do next depends on the results of that reflection, okay? And then we'll check convergence at the end of each step, okay? So here we have some triangle here, right? You have your simplex, in our case, a triangle, right? And what you do is you evaluate the function at all 3 points, okay? And you're going to label the 3 points U, V, and W, okay? Where U is the best performing point, okay? So when you run the function, this gives you the smallest value, okay? And then W is the worst performing point, okay? So you have some kind of function where U gives us the smallest value, W gives us the largest value. The W is the worst performing point. And what we want to do is we want to get rid of the worst performing point with a better performing point, okay? And so our first step is we're going to reflect W, right? So what you do is you find the midpoint of the remaining points. So in our case, that's going to be U and V. We find the midpoint of U and V, and then we reflect W across that midpoint, okay? So basically you just take, what's the vector difference between W and the midpoint, and then you add that to the midpoint and you get your reflection R, okay? And then you evaluate the function at R, okay? And you say, well, is my function R better than my function, at least better than my function V, okay? And if your reflection is not better than V, then then R is going to be your worst performing point, right? R could be better than W, right? But then if it's not better than V, it will still be the worst performing point, right? So let's say U gives us a value of 1, V gives us a value of 2, and W gives us a value of 10, okay? So we say 1, 2, 10, 10 is the worst performing point. So let's change that, right? We reflect it, and let's say R ends up being 8. We go, oh, 8's better than 10. Maybe we should keep that, okay? Well, what are you going to do at your next iteration? Okay, you got 1, 2, and 8, and you go, this is the worst performing point. If you reflect it back, you're back where you started, right? So your reflected point has to at least perform better than V. Otherwise, there's no real point to doing this, okay? So if the cost at the reflected point is better than V, okay, but it's not better than U, then what we're going to do is we're just going to replace W with R, okay? If it's better than V, we're going to take it and we're going to replace it, okay? And then we'll go to the next iteration. We'll check convergence, okay? However, if you reflect this, okay, and the reflection ends up even better than U, right? So this has a cost of 1, 2, you reflect it, and you get, say, 0.5, right? That's better than my best performing point. You go, at that point, we just try to be a tiny bit greedy, right? We say, well, you know what? If moving in this direction worked well, what if we go a little bit further, right? Let's keep moving in the same direction. So basically what you're going to do is, here the distance from W to the midpoint is, some length. We added that point to this here and we get the reflection. We're going to add that same vector from the midpoint W to the midpoint, whatever this length vector is. We're basically going to add 2 of that to get to my extended point E, okay? So this is my extended point. And if we find the extended point is even better than the reflected point, we'll take it, okay? But if the extended point is not better than the reflected point, right? The reflected point is better than U, but the extended point is not better than the reflected point, then we'll take the reflected point. So we have the reflected point, we have the extended point, we say, which one's even better? Which one's better? If R is better, we take that one. If E is better, we take that one, okay? All right. We had the situation where, okay, we said you reflected it, but it wasn't better, right? So what do we do if you reflect W and you get R and it's not better than V, right? And we said, well, we don't want to just take R, even if it's better than W. If it's not better than V, right? Okay, if the reflected point R is not better than V or U, it would be, again, pointless trying to improve the simplex by using the reflected R, right? As this would just become the new worst performing point. And at your next iteration, you would reflect it back and you would just get the worst performing point again, okay? So at that point, we're going to try contraction, okay? We're going to have an inside contracted point and an outside contracted point, okay? So your inside contracted point is 1/4 of the way from W to R, and your outside contracted point is going to be 3/4 of the way from W to R, right? So it's basically halfway from W to the midpoint and halfway from the midpoint to R, okay? This is your inside and outside contracted point. We're going to evaluate the function at both of these locations, both of these contracted locations. And if either of these points perform better than V, we're going to replace W with basically the better performing point. Whether it's the inside point that performs better or the outside point that performs better, we're going to take one of these contracted points and we will replace W with one of these points. Okay, and then we would go to step 6 to check for convergence. Okay, now if all of these things fail, right? If neither of the contracted points work better than V, right? If this is still worse and this is still worse, then what we're going to do is we're going to shrink the entire simplex down towards the best performing point U. Okay, we're going to replace W with W prime, which is halfway from between U and W, and we would replace the second best performing point V with V prime with a point that's halfway between U and V. Okay, because right now U is the best performing point, and we're going to just kind of shrink our simplex towards the best performing point. Okay, this generally only happens towards the very end of your of the algorithm, as it's like continues to kind of perform better and better and things like that. Okay, and then we check convergence. We see, should we stop the program, right? One method is to use the sample standard deviation of the function values of the simplex. So you take kind of, your 3 locations, U, V, and W, okay, and you take the standard deviation, right? And if the function at U, V, and W are all very, very, very similar to each other, right? Meaning your standard deviation of these values is like close to 0. So the function at U, the function at V, and the function of W have all very similar values, then your standard deviation is going to be tiny. And if your standard deviation is below some tolerance value, then your program can quit. Okay. And then and you take your best performing point there of U, V, and W. You're going to take U and say that one's your optimum value. Okay. So here I've got a little animated demo that I made here. Okay. And so let me just kind of, so we're going to play it. Okay, so here's my starting simplex. Okay, this is the 2-dimensional function, and it's got kind of contour lines. Are you guys familiar with kind of contour lines? The idea of like, if you poured water, like in the bowl here, okay, if you poured just a tiny bit of water, this would be kind of the ring that would form. And if you poured in a little bit more water, this would be the ring that it would form. And if you pour a little more water, this would be the ring that it would form, right? And so, so when you see lots of rings together, this is kind of like where it's changing, the steep slope is changing rapidly, or the value of the function is changing rapidly. And so we know that the minimum is going to be somewhere around here. Okay, so anyway, these are my 3 original simplex points. The red point is the worst performing point. And what's the best performing point? Okay, the best performing point is this blue dot here. This is my best performing point. Okay. And this blue and red point, they actually perform almost equally bad, but red performs just a tiny bit worse. Okay, so I reflect it. This is the reflection here. This is just 3 arbitrary starting locations. Okay, I reflect it. This is better. This point performs better than my best performing point. Okay, so what do? What I do next is I say, let's extend it, right? We're trying to be a little bit greedy. We say, this one performed better than this one, so let's extend it. So we do this and we go, oh yeah, this point performs even better, right? This one was the best performing. Now this one's even better because we're even closer to the center here, right? So we evaluate it here. We don't actually know what the contour lines look like. We just have the function at these 3 locations. We evaluate it here. We say, oh, this is better than that. Let's try extending it. Let's be a little bit greedy. And this point performs even better. So we say, okay, let's take it. Okay, so now I colored it green. And let me maximize this. Okay, so I've colored the point green here, and this is going to be my new corner here. And so this is my new simplex. Okay, and now I evaluate again the 3 points. This is now the worst performing point. This is the worst performing point. So I'm going to reflect it. Okay, so I reflect it there. And when I reflect this point performs better than this point, but not better than this point. Okay, and we can see that because this one is inside this contour line, and the green point is outside of the contour line. So this point is better, not better than this point, but it's better than this one, okay? So because it's in between here and here, we're gonna just straight up accept it. And this is going to be my new simplex. And this is now the worst performing point, okay? So now with this, I reflect it. Okay, I reflect it. This point performed even better than my best performing point, right? So this comes in really close to kind of the center of the interval. So I say, let's try being a tiny bit greedy, and we will extend it, right? So we say, all right, let's go this distance. And when I extend it, now I got too greedy. It's not better performing than this point. This point is better. It's not better than this one, okay? So I don't take the extended point, I take the reflected point, and my new simplex looks like this, all right? What's the worst performing point here? The worst performing point is this one, okay? We're going to reflect it across here. And when I reflect it, what do we see? It performs better than this point, but not better than that point. So we're gonna just accept that, and this becomes my simplex. What's my worst point? This is my worst point now, okay? We try reflecting it. When I try reflecting it, it doesn't, it actually does perform better than the next best point. So we take it, okay? This is my worst point. I reflect it, okay? When I reflect it, I get really bad performance, okay? This is not better than either of the points, okay? So because it's not better, we try the two contractions, okay? We contract the inside and outside contracted points, okay? And when we do the inside contracted point, we see this one performs better than this one, okay? And so we will accept this one, and this becomes my new simplex. This is my worst performing point. We're going to reflect it across here, okay? And we say, all right, does this perform better? It does not perform better than either of these things. So what do? We're going to do a contraction, okay? We do the inside and outside contraction points, okay? And we say, which one performs best? This one performs the best. This one gets us closest to the center here. So we're going to take that one, and this is my new simplex, all right? What's the worst performing point here, okay? The worst one is this dot right here, which touches the contour line, okay? We reflect it. When we reflect it, it gets really bad performance. It ends up being outside here, so we're going to do a contraction again. So we have this one and this one. This is better, and so our new simplex looks like this. This is the worst performing point, okay? So we try out this, that's worse. We try our two contracted points. Which one's the best? This one. So we take that one. And this is now my entire simplex is inside this zone. And we're going to try to find where it is, okay? And so it tries the reflection, it tries the contractions, it takes that one, and our simplex is now there, okay? And it tries a reflection, it tries an extension, and it's not good. So anyway, it keeps performing, and this the simplex keeps running, or the algorithm keeps running, and we can see the simplex keeps getting smaller and smaller with kind of contracted points. And I think this is where it stops, okay? As far as the animation goes, but we can see that the next simplex will just be this very small triangle, okay? And so let me just kind of start the animation from the beginning, and you can just kind of see it works, right? So there's an extension, reflection, extension, or reflection, 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 contraction, okay, contracted outside point, contracted inside point, contracted inside point, contracted inside point, reflection, contracted inside point, reflection, contracted outside point, and that's the end of our animation there, okay? And so we can see that the Nelder-Mead algorithm does indeed try to, get somewhere close to the minimum value there, okay? Okay, and so that's the Nelder-Mead algorithm there. Okay, R has a built-in optimization function, and there are several methods from which you can use And the default method for optimization in R is the Nelder-Mead method. Okay. All right. So that's going to wrap up the portion on numeric optimization. All right, we're going to have our lecture on Friday, and on Friday, I'm going to introduce randomization tests and bootstrap tests, and these are methods for us to perform inferential statistics. And so for a lot of you, well, I don't know, did you guys take Stats 10 at UCLA or Stats 13, or did you take AP Stats or intro stats at your community college? I don't know what you guys did, okay? But not everybody took Stats 10. And so I like to spend, about half an hour just reviewing some important concepts from intro stats, right? So everybody had to take some kind of intro stats course, whether it was AP Stats, intro stats at your community college, or Stats 10, or some equivalent of Stats 10 here at UCLA. And so because what we're going to do is we're going to do inferential statistics on Friday using the computer, doing either bootstrap or randomization tests. But if you don't have a good concept of inferential statistics, then we are in trouble. So here's my my pop quiz. Can anyone give me the definition of a sampling distribution? Any volunteers for what? For example, what is the sampling distribution of the sample mean? Okay, no volunteers. Well, okay, well, in that case, I'm glad we're doing this little review here. Sampling distribution of the sample mean might be normal. It might be normal, just mu. Okay, it is the distribution of all possible values of the sample mean, X bar, Y bar, whatever letter you're choosing. It's the distribution of all possible values of that sample mean that is possible from all possible samples drawn from the population. Okay, all possible samples of a given sample size. Okay, so anyway, let's just do a quick review of inferential statistics and some ideas here. Okay, so first, let's just review what the mean and the median are. Okay, and you guys already know what the mean and median are. These are like measures of center, right? But the key here, and I don't know if anybody presented the mean and median as these ideas. The median balances the number of points that are lower or higher than the median. So wherever your median is, you have an equal number of points below it and an equal number of points above it, right? That's the median. I think you guys know that. That's your 50th percentile. But did anyone explain that the mean balances the deviations of points that are below or higher than the mean, right? So the deviations being the distances from each point to the mean below it equal the distances from the points above the mean to the mean, okay? And because the mean balances the deviations, the distances, that is why it gets pulled in the direction of the skew, okay? And so, a lot of times if you have a skew distribution, the median might be preferred because the mean gets pulled in the direction of the skew. So here's kind of a picture here, right? So let's say you have these 6 points, 1, 2, 3, 4, 10, 10, okay? The median balances the number of points above and below the mean. We got the median would be at 3.5. You would have 3 points below the mean, 3 points above the mean, okay? Where is the mean? Okay, well, you can just say, well, to get the mean, you add up the values and you divide by how many points you have, right? You do 1, 2, 3, 4, and that gives you 10 plus 10 plus 10. So you get a total of 30. You divide by 6 and you say, oh, my mean is at 5, okay? But what the mean is doing is it's balancing the deviations below and the deviations above. So if you draw your line for the mean at 5 and you say, okay, what is the distance to all of the points below the mean, okay? To the points below the mean, we have 4, which is a distance of 1, 3, which is a distance of 2, 2, which is a distance of 3, and 1, which is a distance of 4. And so the distances from 5 to these lower points is 1, 2, 3, and 4. You add those up, the deviations sum to 10 over here. Okay, what are the deviations above the mean? Okay, from 5 to 10, okay, we have a deviation of +5. And from 5 to 10, we have a deviation of +5. Okay, and so the deviations above the mean add up to 10. Okay, so the mean balances the deviations. So you're going to have, here we have 10 above, and the deviations below, we have 10 below, right? So you have 10, 10, and 10. Those balance out, or I guess -10 and +10. Those balance out to 0. Okay, so that's what the mean does. The mean balances the deviations. Okay, and we also have the variance and the standard deviation, right? And so these are measures of spread, right? And so spread is basically how similar are your values to each other, or how different they are from each other. So if you think of a second grade classroom, the students in a second grade classroom, pretty much everyone in that second grade classroom at the start of the school year will be like 7 years old. Okay, maybe you have one 8-year-old, maybe you have one 6-year-old or something, but pretty much everybody in that classroom at the start of the school year should be something like 7 years old. Okay, and so you have very little spread in ages there, because pretty much almost all of the values there are very similar. Okay, whereas if you were to go to, say, the DMV, right, the Department of Motor Vehicles, where you have to renew your driver's license, your vehicle registration, or things like that, what are the ages you have there? You've got all kinds of people, right? You've got young people, you've got old people, you've got seniors, you have babies, you have adults, you have all sorts of different ages there. So you have a very large spread in your data, okay? And basically the variance and standard deviation, these give us numbers rather than just saying, oh, there's lots of spread and there's little spread. We can say, oh, the standard deviation of ages in this room is 0.3 years. The standard deviation of ages in this room is 17.5 years, okay? And we can have a description of how spread out the values are, plus or minus, in either group, right? We can think of the variance as the average squared deviation from the mean, meaning if you think of the definition of the variance being x minus x bar squared over n minus 1, right? So, you know, x minus x bar, this is basically our deviation from the mean, okay? And x minus x bar squared would be the squared deviation, okay? And then if you sum up and you divide by n, that would be the average, okay? But here we're dividing by n minus 1, so here I'm putting in quote average, right? So it's pretty much like the average squared deviation from the mean, but it's a little bit off. You're dividing by n minus 1, right? And this is what you guys learned about this, right? Bessel's correction, in, maybe you haven't done it, in 100B, like why we divide by n minus 1. Why do we divide by n minus 1 rather than n? Anybody? Well, if just n is biased, why is just n biased though? Yeah, that is true. If we divide by n, it's biased. Anybody know why? Okay, well, the reason why it's biased, okay, so if we knew the population mean, okay, we could just do x minus mu squared divide by sigma, or at sigma, and then add them up and divide by n, okay? If we knew mu, okay? If we knew mu. But the problem is we don't know mu, so we're using x bar, right? And x bar is what? It's based on our samples observations. And of course, because x bar is coming from our own sample, it's going to underestimate the deviations from the mean, right? Because the mean of our sample is going to be right in the is going to be the spot that balances out the deviations. And so you know, your sample might be a little bit higher, right? Your sample might have a mean that's a little bit higher than mu, okay? And so if you were to calculate x minus mu for the true value of mu, you know, all of your deviations would be a little bit bigger. But because you're using x bar, which comes from your own sample, these square deviations, the overall square deviations end up being estimated to be a tiny bit lower. And it turns out the amount of compensation you need is exactly n minus 1, okay? So yeah, using n is just biased, and it's because you're using your own samples, right? It's like, it's, you know, if you're basing your opinion of the world based on what, you know, your own sample, what you viewed, your opinion of the world is going to be biased, right? It's just based on what you've seen and not truly what the world looks like, right? What the average world looks like. So, okay, other key ideas here. The normal distribution. I think you guys are all familiar with the normal distribution, unimodal, symmetric. And the key thing about the normal distribution is that values near the middle show up most frequently. Values far away from the middle show up less frequently. And if you do and overall values, z-scores above 2 are considered unusual. Z-scores above 3 are considered highly unusual, right? Okay, so so that's what we've got. Okay, that's the normal distribution. All right, I think you guys all know that. Oh, I forgot, I put this slide here. Okay, so 68%, about 2/3 are within 1 standard deviation of the mean. Around 95% are within 2 standard deviations of the mean. So more accurately, you know, 1.96. You guys should all know that number, right? 1.96 gives us the middle 95%. And then 3 standard deviations gives us almost everything, 99.7%. And that gives us almost everybody, almost everyone's within 3 standard deviations. And if you're more than 3 standard deviations away, we say, you know, that's really unusual, okay? All right, and so when we do inference, the whole idea of statistical inference is that we want to make conclusions about the population being everybody that could help us answer our question, right? So if we have a question, you know, is experimental drug XYZ effective at treating disease JKL, whatever it is, okay? Then the population would be everyone who has this disease, everyone with disease JKL, right? And the whole point of statistics is that we can't study everybody, right? We don't have unlimited resources. It costs money to conduct a survey. It costs money to do any kind of experiment. And so we can't survey 1 billion people, right? How many billion people are there in the world? 7 point something billion. There's a lot of people. We can't survey and study everybody, right? And so we're only gonna study a sample. And the idea is we wanna draw inferences about the population based on our sample, right? So this is kind of my picture. This big potato looking thing is supposed to represent our population. It's too big for direct study, right? And so what we're doing is we're drawing individuals from the population. This creates what we call our sample, right? We're going to look at our sample. Based on our sample, we try to say, this is what the population looks like. Ideally, the sample we select is going to be representative of the population, right? And so one method that should give us a representative sample is random sampling, but it's not guaranteed to make a representative sample. And random sampling is actually really, really hard to pull off, okay? It's not guaranteed to produce representative samples. And on top of that, random sampling is really hard to do. But kind of all of our statistical methods is based on this assumption that we're able to do random sampling. And maybe it's a bad assumption, but if we don't make this assumption, like, we can't really do any math, okay? Because everything's kind of based on this idea of randomness. So the idea is, you know, in practice, getting a truly random sample, maybe it's impossible, maybe it's really hard to do, but hopefully the sample that we do have, we can kind of treat as a random sample, okay? And if we can kind of treat it as a random sample, we're probably in good shape, okay? And all right, so at the very beginning of this section, I said, what's the sampling distribution? And we didn't have a whole lot of volunteers for what the sampling distribution is. But the idea is that when you take a random sample from the population, right, and you calculate the mean of your random sample, the mean of your random sample for one person, like, you know, if one person takes a random sample, they might say, oh, okay, the mean of my sample is 15. Okay, someone else takes a random sample, maybe same number of people, but because they got a random group of people, maybe the sample, their sample has a slightly different mean, right? 15.5. And if somebody else takes a random sample, maybe their sample also ends up being a little bit different. Maybe they get 16.2. Okay, so every time you take a random sample, because the individuals you select in your sample are going to be different because they're randomly chosen, when you calculate the mean of your individuals, you're going to get slightly different mean values, right? And so which sample means are going to be more common? Which sample means are going to be less common? Okay, well, some of them, you know, we expect it to follow a, well, the central limit theorem says, you know, this thing should look like the normal distribution as long as these conditions are met, et cetera, et cetera. But what that distribution is called the sampling distribution of the mean. It basically tells us what sample means are more likely to occur and what sample means are less likely to occur. Okay, and kind of the key here is that the mean of your sampling distribution will be the same as the mean of the population, and that the standard deviation of your sampling distribution, which we call the standard error, is going to be have a value of sigma divided by the square root of n, right? So we can create a sampling distribution via simulation. We just start off with some hypothesized population, and we give it some shape. So if we just say it's normal and it has a mean of 0 and a standard deviation 1 or something, what we're going to do is we draw one random sample, calculate the mean of that sample. Okay, we do it again. We draw another random sample and we calculate the mean. And we're going to calculate the mean and record the mean of every single one of these random samples. We do this again and again and again. So maybe I do this like 100,000 times. I have 100,000 different random samples. I have 100,000 different means of different random samples. And then we're going to just keep track of all of those sample means, 100,000 sample means, and that will give us basically a simulated sampling distribution. And again, the key here is the central limit theorem says whatever that your sampling distribution is going to have a normal distribution centered at the population median, right? So here's our population. I'm drawing a random sample of how many values? 13, 14, 15, 16. 16 values, okay? I draw 16 values from this population. So the population has a standard deviation of 1. I draw 16 values. So these are my 16 values shown here with the little rug plot here. And I say, okay, what's the mean of these 16 values? The mean of these 16 values is 0.92. I'm sorry, 0.092, 0.092. I'll take another sample of 16 random values, okay? So these are my 16 random values. I got negative 2.31, 1.98, a bunch of different values. The mean of these 16 values is 0.096, okay? So just ever so slightly different from the previous value. Here's another 16 random values, okay? These 16 random values give me a mean of negative 0.197. Okay, so the mean of these 16 values gives me a mean right there. Here's another mean. This mean, just by chance, I get a mean of 0.426, right? And here's another one. Okay, and so here, again, these are just a whole bunch of different sample means from different samples of size 16. Okay, and so I can simulate this. I guess not 100,000, I'll do 10,000. 10,000 different random samples of size 16. Right? And so this is just some very, very quick code running a loop, right? So I'm going to create a vector of length 10,000. I do sequence along. So basically from 1 to 10,000, we're going to draw 16 values from the standard normal distribution. Our norm produces values from the standard normal, mean 0, standard deviation 1. that's going to be random sample. I'm going to calculate the mean of my random sample, store that mean value into slot I. So from slot 1 to slot 10,000 in my vector sample underscore means. Okay. And when I do that, the mean of all of my sample means, so the mean of my sampling distribution is very close to 0. And the standard deviation of my sample means, of my sampling distribution, is very much like 1 divided by the square root of 16. So 1 over 4 gives me 0.25. Okay. And here's a histogram of my sampling distribution, right? Histogram of the, I guess, simulated sampling distribution. Mean of 0, standard deviation of 0.25, and therefore about 95% are between 0.5 and negative 0.5. And, you know, almost 100%, 99.7% are between negative 0.75 and positive 0.75. With just a few values outside of that range. Okay, and again, if I say, you know, does it follow a normal distribution, I can create a QQ plot. So if I plot the theoretic quantiles against the quantiles that appear in my sample, we pretty much get a straight line, maybe a couple things that are a little bit off, but pretty much what we get. And so that looks good. And the key idea there is that the central limit theorem, oh, I actually even have this little toy I want to show you guys that shows us that, yeah, when you do this, you get something that looks like the normal distribution. Okay, and so here is, here, let me stop sharing my screen for a moment here. All right, can you guys see this? Okay, so this is a little practical toy showing the central limit theorem. The idea here is, so you can kind of think of this as almost like a binomial distribution, but central limit theorem. So the idea is there's all these little beads or marbles or whatever, these little tiny little beads here, and they're going to come out through the funnel, right? I'm going to flip this over. They come out through the funnel, and every time they hit a peg, they can either go to the left or go to the right. Okay, and so you can think of going to the right as being like +1 and going to the left being 0, right? So either and so you can either get all the way to the right, and that would require you to, every time it hits a peg and it goes to the next level and goes to the next level, it would have to go right to end up all the way to the right. Okay, all the way to the left, I would have to go left, right? What about ending up in the middle? I can go right, left, right, left. There's lots of little different paths to end up in the middle. And so what we see is that if you think of this as just kind of either adding +1 or 0, most of the time you'll get an average of something around 0.5. Okay, and so again, if I flip this over, what we'll see is that the beads will fall and it fills out something that looks a lot like the normal distribution, just by kind of just by nature, right? So it's kind of fun for me to do this. Okay. All right, so there you go. Okay, so that's the these are like stats toys. Okay. What was I doing? Let me share my screen again. Okay, so the central limit theorem says that the mean of a random sample comes from a normal distribution centered at mu, which is the population mean, with a standard deviation of sigma over the square root of n. And so when we draw a random sample, there's going to be a 95% probability that the mean of your random sample is going to be within 2 standard deviations of the population mean, standard deviation being sigma over the square root of n. Okay, and so we can use this to create a confidence interval. Okay, and so when we create a confidence interval, what we're doing is we're observing a value x bar, and we're saying where is going to be mu. So it's kind of flipped around. So the sampling distribution said if we know where mu is, we know 95% of the time x bar is going to be within 2 standard deviations of mu. Okay, and now we're flipping that around. We're going to say, well, I don't know where mu is, but I know x bar is here. If x bar is here, I can be confident that mu is within 2 standard deviations of x bar. Okay, but then But the trouble is we don't know what sigma is. And so what do? We estimate sigma using the sample standard deviation, S, rather than sigma, okay? Right now, and that's reasonable, right? If we don't know what the population standard deviation is, we say, well, what do you think the population standard deviation is? You say, well, I think the standard deviation is something like the sample standard deviation. So we use the samples standard deviation, okay? And because that introduces extra uncertainty, rather than using 1.96, we end up using the t distribution, which compensates for that, right? You end up using numbers bigger than 1.96 based on your degrees of freedom, okay? The other side is hypothesis testing, okay? Oh, and I might go a couple minutes over our time here, okay? In hypothesis testing, we write a hypothesis, right? Some null hypothesis that says, this is what the population looks like. The null hypothesis says, the population looks like this. It's got a mean equal to this, okay? And we say, well, if that's true, what kind of samples should I get, right? What kind of sampling distribution should I have? And we are going to look at our data and say, does my data align with what the hypothesis says, right? We're testing the hypothesis against our data. So if we do something like the t-test, there's two independent sample t-test. We're comparing the means of two populations. And your null hypothesis starts off by saying, population 1 and population 2 look like this. They have the same exact mean. The means of population 1 and population 2 are the same, that there's no difference between these two means, okay? And if that were true, then whenever you take a sample from population 1 and a sample from population 2, we would expect the means of those samples to be equal to each other, okay? And we know that that's not always the case, okay? We know that sometimes when you take a random sample, you get a sample that's you get two samples where the two means aren't exactly the same, okay? And so we do calculations and we calculate your p-value. And the p-value is, all right, here in my sample, the two samples, let's say, had a difference of, I don't know, some number of points, right? 3 points, okay? The question is, could that happen just by random chance? Is it possible that I get two samples where the difference between them is 3 points just from randomness, right? And if so, what's the probability that that happens, okay? And that's the p-value. The probability that I get some data that looks like what I got, if the null hypothesis were true, that's equal to the p-value, right? So, so again, if we have two hypothetical populations with the same mean, when you take random samples, you expect both of those samples to have sample means that are approximately equal, okay? Your observed difference is x bar 1 minus x bar 2. This is the mean of sample 1 and the mean of sample 2 from your observed data. And it's probably not going to be exactly equal to 0, right? It's not going to be exactly equal to 0. And the question is it significantly different from 0? And so, you know, what's the probability? Here's the p-value, right? If the two populations were equal, as in they have the same mean, what's the probability that just from random sampling, we get two samples where the difference is equal to or greater than this observed difference, x bar 1 minus x bar 2, right? So the null hypothesis is just a silly example. Population 1, population 2 have the same mean. This is what your null hypothesis looks like. You collect some data. X bar 1 is 10, x bar 2 is 12. So your two samples have a difference of 2. The question is that difference significant? Okay. And the answer is going to depend on the standard error, right? If the standard error is tiny, right? Let's say the observed difference of 2 is, say, something like 5 times the standard error, we'd say, oh yeah, that difference of 2 is a big deal, okay? On the other hand, if the standard error is a big number, and this difference of 2 is, say, only like 1.2 times the standard error, like, oh, you know, this difference of 2, not that big of a deal, right? And so the p-value quantifies exactly, you know, what's the probability of getting our data if the null hypothesis were true. Getting our data or something more extreme if the null hypothesis were true, okay? We are going to compare our p-value to some arbitrary significance level alpha. to decide if the p-value is big or small. If the p-value is small, what that means is it is very unlikely to get our data if the null hypothesis were true. Okay, it's very unlikely to get our data if the null hypothesis were true. So therefore, the fact that we actually got this data, which is, hypothetically shouldn't happen, right? If the null hypothesis were true, it's basically saying I shouldn't get this result, okay? And somehow it happened, okay? What we're gonna say is the reason why I got this is because the null hypothesis is actually wrong. We're gonna reject the null hypothesis, right? Because if the null hypothesis were true, I shouldn't be getting this data. This data should be like very, very improbable. And the fact is I got the data. So how did I get this very, very improbable data? Oh, well, that's simple. Just the initial assumption that the null hypothesis makes is wrong. Okay, and that's what we do. Okay. On the other hand, if the p-value is large, it just says, oh yeah, if the null hypothesis were true, you might get data like that 30% of the time. So you got that data. Well, it's not that weird. It doesn't sound weird to me. And that's basically that. Okay, so we say I have no reason to reject the null hypothesis. It doesn't prove that the null hypothesis is true, but it just says, yeah, if the null hypothesis were true, you might get this data like 30% of the time. And so the fact that you got this data, yeah, that's not that weird. That's not that weird. It seems pretty normal to me. It's not a big deal. So we have no reason to reject the null hypothesis, right? If the null hypothesis says, hey, yeah, this data should happen only 1 in 1,000 times, and you got it, you can go, oh, am I that lucky 1 in 1,000? No, probably not. It's probably the fact that this initial assumption is wrong. And so you would reject the null hypothesis when your p-value is small, and you don't reject it when the p-value is large. Okay, you know what? So all of these things that we've talked about and what you did in your intro stats class, those were parametric hypothesis tests. They used the central limit theorem. They used these parametric distributions, the t distribution, the normal distribution, okay? And you probably had to prove the central limit theorem in stats 100b and stuff like that. You had to check your conditions to apply the central limit theorem, okay? And what we're gonna do in our next lecture is we're gonna introduce randomization tests, also the bootstrap test, where we're not gonna rely on these parametric assumptions. Or, I mean, we have a parametric bootstrap, so there's a little bit of parametric stuff. But, I'm already over my time, so I'm gonna go ahead and, give you your last view quiz answer, and then we'll end our lecture here, okay? And then I'll just do these last few slides on Friday's lecture. So last view quiz answer is A as in apple, A as in apple. Okay, A as in apple is your last view quiz answer. All right, thanks for your patience. Thanks for sticking around for a few extra minutes here. I will send out an announcement for the exact time that we'll do Friday's lecture. It's going to be at noon on Friday, I'm pretty sure, but it's a slight possibility that the schedule changes a little bit. But on Friday we'll do the last bit of kind of new content, and then you'll have a few days to study for the final exam. All right, thank you everyone. Have a good night, and we'll see you guys on Friday.